Okay, so we see the expression we have to integrate. Antiderivative of 1 minus t quantity to the fourth. You can do this with u substitution if you want, but just intuitively, you know it's linear, so it's probably going to be a fifth power of 1 minus t divided by 5. Now, since you have the 1 minus t, let's just write down 1 minus t quantity to the fifth over 5. What's the derivative of that? Okay, I've got a negative sign in front of it for reasons we'll see in a minute, but just take the derivative of that without the negative sign. Well, you're going to get a 5 times 1 minus t to the fourth, but you're going to have to multiply that by -1 because of the chain rule. You're chaining the fifth power function with the 1 minus t function, and the 1 minus t function has derivative -1. So you have to have a negative in front of this if you want to end up with this when you take the derivative. Now you can do a u substitution, and that's trivial. So you can do that if you need. And if that's not trivial to you, then you need to sit down and do it. You need that much integration technique for the rest of your life. Okay? Similarly, 1 minus t cubed has antiderivative negative of 1 minus t quantity to the fourth divided by 4. That's going to occur here also. So we're going to have this antiderivative evaluated between 0 and 1. And of course, that function is times I, so the result is going to be multiplied by I. And then the same with this function, multiplying the result by j, and here this result by k. And then we're going to dot that with -j minus k. And the result of that is going to be -1. And I'm not going to work that out for you. Just substitute in here and see how it works. I would recommend you start with this and integrate it by whatever technique you would have used if you hadn't seen what I did, and verify that this integral is -1. Very simple integral, good practice. Won't take you but a minute or two. And if it does take you more than a minute or two, it's because you need the practice, so you should do it regardless. Okay, well, that's all well and good. Now let's just think about something. When we went from here to here, from 0, 0 up to the 1, 1, 1 point, our integral was 1. Now going from 1, 1, 1 back to the x-axis at 1, 0, 0, along a straight line we get -1. So that the total integral from here to here and then down to here is 0. Okay, two things about that. That integral should be equal to the change in the original function. Okay, now the original function had what value at the origin? Well, 0. All these were zeros. What value at the point 1, 0, 0? Well, both y and z were 0, so the value of the function was 0. So the value of the function changed by 0. Okay. This illustrates, at least for this example, that integrating from one point to another, the gradient of a given function, the integral is equal to the change in the value of that given function. Now, since the value of that given function was 0 and there's so many zeros floating around here, it's not a particularly impressive demonstration. But that's something you want to kind of keep track of, okay? And the other thing is, and there was no guarantee. I mean, the integral from here to here was 1. Why would you expect the integral from here to here to be -1 if you didn't know about this? You know, you wouldn't expect that, but you find that it's true. So you find that the total integral is 0, which is the change in the value of this function. The other thing is that, and it's much related to that, the integral around a closed path then has to be 0. Because the closed path ends where it begins, so this function doesn't change, right? And if we integrate from here to here to here and then back to here, we're going to get 0. Because from here to here is 1, from here to here is -1, that gives us 0. And from here to here, x is 0, so the value of this gradient function is 0 everywhere between these 2 points. So that the line integral from here to here is going to be just plain 0. Well, those are really important ideas. So I'm going to expand on that just a little bit more.